Hello friends, welcome back to another video on this channel. In today's video, I will be showcasing this. This is what I am calling PillFlight, which is basically a full-fledged flight controller equivalent to the commercial stuff you can buy which run on Betaflight but running on an STM32 F411. As you can see, this is not a F405 but an base. This is even a minimum systems board F411. Now, the goal of this project was to actually build a software which you can deploy on any bare F411 chip with the most bare minimum hardware to get a flight controller which is actually very decent and quite comparable to some of the commercial stuff you can buy, but without obviously having to buy the commercial stuff either, because on one hand this is obviously a lot cheaper than the commercial hardware, but also simply to learn about this. Now, the core system of this is obviously, as you can see, we have multiple chips. Now I'll walk you through everything, and also I'll tell you right now, none of this is actually hard coded. You can configure everything you want in the software, which I'll also walk you through shortly. So first of all, if we look at the front here, you'll see there are two gyroscopes. There is the MPU 6050, this one, and an MPU 9250 or a 6500. So now the thing is actually this has a failsafe gyroscope system, or sorry, a failsafe IMU system, where basically this here is the primary IMU acting as the primary IMU, and if that fails for whatever reason in flight, so if it's giving stale data, let's say it disconnects, or even if I completely remove it and start, I can do that as well, then it will immediately in flight fail over to this one, which is also configured to be able to basically auto land, or at least be enough to land it without crashing it and breaking the drone obviously. Or in another case, if for example for some reason one of these fails, which obviously this is not the most reliable chip, and in fact most 9250 nowadays are actually fake because official 9250s have been discontinued. So in that case also you can still fly the drone if you say for example take it to somewhere on the backup IMU as well. Now the other chips here, you'll see a BMP 280 barometer for altitude hold, and yes, this does have a working altitude hold as you saw in the video. I'm not sure if you saw it very cleanly, but the middle there, that was an altitude hold when it was sitting there. I turned it off quite quickly just to show you that what happens. So I'll talk you more about that and why it almost immediately went up again. So I'll tell you more about that as well. Now obviously you can see a compass here. Now this is, even though this says an HMC 588 as with the MPU 9250 here, this is the same thing. This is actually QMC 588 not an HMC 588 because officials are now being discontinued, and this is a VL50 LOX. This is the TOF sensor, a time of flight sensor. So basically this is a laser sensor which simply sends a signal down and gets the exact precise distance. So what I'm using this for is actually auto land. That's basically it. Now I'll tell you more about all of this in a second. But one small note for this, you might be wondering why I'm not using this for altitude hold, is because this particular chip, and in fact another one of the chips that I bought, both of them are actually not functional properly. They advertise to have a range of up to 2 meters, but in my case anything more than 180 millimeters or 18 centimeters, which roughly is about the height of the legs plus a bit, is not reliable at all. Like it just goes down, in fact, according to the sensor rather than up in distance. So I decided to use this for a precision landing feature instead of using it as an altitude hold feature. So that covers actually what configuration I have. Now this other thing here is simply just a voltage divider. This is literally just effectively two resistors put in parallel and then you bridge off of the middle one, which is by definition what a voltage divider is. This is just to give telemetry to the flight controller about what voltage the battery is at, and then send it back to the receiver and then to the the transmitter here. Now I'll tell you all about that in a second as well. And another thing is this has both a display. Now I'll put this back in here just because otherwise it will show fail. Also I'll show you what happens when it fails in mid-flight as well. Now this is the SSD 1306, I believe it's called. This is a simple OLED screen just for configuration. You do not need this to fly at all. In fact, in flight it is disabled to save CPU space for the this F411, because obviously it's not as powerful as an F405, which is what commercial flight controllers use. Also we have a joystick here, simple joystick, just one joystick and a button for configuring everything on this, and it actually has its own menu as well. I'll show you that as well in just a second. This here is just a simple 3 MOSFETs. These I believe are the IRFZ44N MOSFETs, which are N channel MOSFETs. These take 5 volt from the this guy and controls the 12 volt LEDs, which you saw down here are the LED strips. These are simple 12 volt addressable RGB LED strips. Sorry, not addressable, but basically each of these LEDs has all the 3 colors, so it's much better than the normal LED strips you will find on the market. Now, for this particular build, unlike the last drone build I showcased, you do need an IA6B or other SBUS or PPM compatible receivers, because the sheer number of things on this drone is way larger than the other ones. So because of that, the number of pins are less, so simply there isn't enough pins on the chip to reliably handle proper, like just literal PWM signals out like we did for the other one. You do need a SBUS, and also it's more reliable. Plus another benefit is, if you would know, the i6 is marketed as a 6 channel receiver, but if I go over here and go into my display, you can see here this particular one has the modified firmware which allows it to have 10 channels. As you can see, look, this is channel 9, this is channel 10, channel 6, this is 8, that's 7, that is 5, then this is obviously 3 throttle, this is 1, 2, and this would be 4. So this actually it has 14 channels. If you look down here, it doesn't have it on the display, but this guy actually has 14 channels, up to 14. So yeah, the i6 is actually capable of transmitting up to 14 channels. It's restricted by the default firmware, so you can flash this very simply. There's a lot of guides available in the internet about what you need to flash one of these. Also, with this flash, what you get is a reverse telemetry feature. So instead of just normal i6 hardware which sends signal from this to the receiver, this guy actually allows you to send signal back from this down to the i6, so you can get status of the flight controller in flight, such as the batteries, the roll, pitch, etc. I'll also show you guys that in just a second when I turn this on. Now, before that, I'd like to talk about wiring a bit. Now obviously you can see this is a lot of wiring here. There's a bunch of wires. Now before I go to the physical wiring, I would like to first show you one thing, which is the actual file which you will be reading from. Now when you download this, you will get something like this when you go to the GitHub and download the code. Over here you will find in, I believe, docs, yes, you'll find both a journey.md and a wiring.md. Now this is something that is just a little personal note. I have VS Code over here, so this is just a simple personal note, and you will find that this just shows the journey of this drone from crashing it. And obviously if you are trying to build a flight controller by yourself, you will crash it once or twice, and in my case it was a lot more than once or twice, but this showcases the journey of how we started and where we are today, which is a fully functional and flying flight controller with a working altitude hold and a heading lock feature. So I think that's pretty cool, and I recommend you should read through this once, just for fun. But more importantly, here we have a wiring.md. Now this is the more important thing. This is actually what you will use to wire everything. Now I mentioned before everything is configurable, so let me first just show you that, and then I'll talk about the wiring. So first of all, the options you have, in my case at least, because I had limited hardware, and this is where the open source part kind of comes in. I would like people to get more hardware and hopefully add on to this with more chips and stuff in the future. But in any case, in my case, I only had 2 IMUs. Now the main configurable thing for this is basically, at the minimum, what you need is simply a IMU and a microcontroller. That's it. You don't need anything else to get it to fly, right? Obviously that's the bare minimum. Everything else is actually removable. So in this case, as you can see, this whole subsection, which is the backup gyroscope, the compass, etc., everything is on a separate board. Even if I remove this, it goes to fail, but automatically it knows that because everything else is failed, it will switch over to primary IMU mode, and it will just use the primary IMU and fly the drone, which will disable obviously all heading lock, every other feature, but the drone still flies. So that is at its core what this was supposed to achieve, is configurability to you. Now in our case, what options you have is over here as a primary IMU, you can either have a 9250 or a 6050, and it even has the option of putting it either on I2C1 or you can have it on SPI if you have the 9250 or 6050. Now that goes both ways. So if you have the 6050, for example, you can obviously only use I2C1, but for the 9250, both I2C1 and the 6050 are enabled. So if I look over here on the configuration, now this is actually the flight. This you will find in core inc, and then you'll find it right here, fc.config, fc_config.h. This over here you'll see is you can set your primary and backup IMUs. So ITC2, MPU 650 and MPU 6500 on SPI2. This is my current configuration, which is flying as you saw in the video. Now you can set this to I2C1, you can set this to I2C1, whatever you want to do. It is all up to you what you want to fly with. Now I would recommend setting a separate bus for your primary and backup controllers, backup IMUs, sorry. And also more than that, I'd recommend using SPI and ideally a 9250 or a 6500, because it is actually a lot faster. So instead of 400 megahertz, it goes up to 8 kilohertz, which is a lot faster than the I2C can handle. And obviously the 9050 is also less prone to vibrations and other noise, which makes it a cleaner base to use. And obviously above that there's a lot of like filtering going on. There's a low pass filter, multiple low pass filters for both the accelerometer and the gyro. So you can read all about all this actually, because obviously when we started none of this was there. So all of this is actually just from simply flight testing and other testing tools, and there are a lot more testing tools as well, which I will tell you about shortly. But the most important one is you can configure this and fly it. So that's and everything else you'll find here. So now the way I have it set up is obviously the most important things are here. Now other than that, every other thing is on I2C2. So the compass, the barrow, everything else is on I2C2. They are not configurable because I feel there's no real need to add that complexity in. It's just the IMU that matters, because that is the most important thing. Everything else can just be on the backup bus, and if it works, it works. If it doesn't, it doesn't matter for the core flying of the drone, which is obviously the main objective. Now more things you'll find here are, for example, the USART TX, which is obviously the one which will be used by USART RX, which will be used by the the receiver to like read the actual inputs from the transmitter and by the flight controller. Now also other than that, you'll find the other things such as the USB buttons and all that, the joystick buttons and the stuff like, for example, the what's it called, the this thing, voltage divider, etc. Everything you'll find in there. So this is a proper wiring guide you'll find here. There's also the recommended things which you should bridge, the recommended power voltage, everything from the strips, the LED strips, etc. Everything you'll find in here. Even you'll find here the power and ground topology. Everything you need is all here. So that is the first and most important thing. Once you follow the wiring guide and wire up this flight controller and configure it based on what you want. Now once you are done with all of that, first of all, I'll just turn it on here. Now this has a very special configurator as well, like MultiWii or BetaFlight. So you can see when I plug it in, first of all the display shows up. Now as you can see, this guy started beeping. The reason it's beeping is because the voltage divider is actually reading 0 volts, because there's obviously nothing connected. So my main battery which I was using in flight is charging there. So I'll just quickly connect up the other battery. This is my backup battery in this case. No, sorry, it's a bit hard to do with one hand. As you can see, it starts going. Now it has a failsafe where if you start it with the thing armed, as you saw I had it, it will not arm and wait until you first disarm it, then only it will let you arm. Now obviously I won't arm it now. I'll also tell you a bit more about these in just a second, but for now, as you can see, this is the lighting knob. So as you can see, this is controlling the lights. Now this is the flicker mode, which is like the sort of Airbus mode. This is a scale knob. So basically these inputs are scaled to the level. So I'm moving that knob. As you can see, the SC value is moving up and down. So that's how much authority, basically, like moving this here, how much authority that has depends on that scale value. This is obviously, as I said, arm. Low, the like when it's down, which is actually high, is disarm. The reason for that is simple. When you are flying it, when it goes up, it's much easier to do this and disarm it quickly than do this and disarm like that way and disarm it. So it's just a convenience thing, really. So you can quickly disarm if something goes wrong. This is heading lock. Down is locked, up is not locked. As you can see here, you'll see a HL logo pop up. Sorry if it focuses. Yeah. As you can see, that's heading lock. This is the mode. So as you can see, currently it is in angle. I can move it to horizon and acro. Also, I would not recommend flying it in acro because obviously the flight controller, well, it works, but you know, it's a big heavy drone F450, so flying it in acro isn't really feasible. This is altitude lock, enable and disable as well. Rest everything is normal. Now the things I told you about the reverse telemetry. So things that we receive from this are simply all the most important things. So roll, pitch, heading. If I move up, you will find this is the DPS. So basically this figure, as low it is the noise. It's sort of like the noise floor basically of the primary gyro or the gyro in flight or in use, sorry. So the lower this value is the good. This jumps to about 20 in flight, which is fine because this is not the most well vibration dampened drone in the world, and also not the most flight hardened flight controller as well. Other data, you'll see TX voltage. So this is the voltage of the transmitter. Int voltage, or this is internal voltage basically. This is the voltage that is being read by this pin here. Over here, as you can see, this is the power coming to the receiver. Now this comes from XY3600, I believe this is called. It's a really lovely chip, really lovely buck converter that converts 12 volt of the this thing, the LiPo, down to 5 volts for use both in feeding into the this guy, the microcontroller, the flight controller, as well as feeding from, in my case, into this guy, which is the voltage divider because it has its own separate power 5 volt requirement as well, and into the receiver. So that is that 5 volt being read here. If you move further, you'll see mode here. Now stab is actually stabilized mode, so both horizon and angle mode is stabilized. This is acro. I'll obviously not arm it because it'll show here armed, but it'll spin up the flight, this guys. Now actually one thing I'd like to show here is the menu. So when you click the button, I just click the button on this, you'll find a settings menu pops up and you can scroll through it. Now this important stuff like gyro calibration, compass calibration, orient calibration, primary axis, reset cal, everything is self-explanatory. I'd just like you to go through it and find it out. I won't go through much of this because this is pretty self-explanatory things. Motor test, LED test, PID tune, everything here is pretty self-explanatory. Now one thing I would go here is in PID tune, there is a Mahony filter running on this. I started with a CF, so the top values here were for the CF which were running initially, but the bottom values are for the Mahony. That is actually switchable in the configurator. So if you use CF, use these values, tune the upper values, otherwise just tune the lower values. Now if your drone is not stabilizing very well, if it's too sluggish, you should increase the roll and pitch R, this level R and level P values. Otherwise, if it's vibrating too much, reduce the dampening, increase the dampening values. And this Mahony KPKI is just lean. So if it has a bit of a lean, then for example, it always stays a bit like this, even though you calibrated the gyro, then just increase those standard PID tuning things. But I thought you should know this. Other than that, obviously you can get all the sensor readout, raw sensor readouts here of all of them. Now the dry run mode, this is the one I was talking about. So in this case, what happens is everything works like it would in actual arm mode, but the actual motors are muted. So now if I arm it, as you can see, it starts flickering the lights like the Airbus mode. And also, as I said, if I move it to the thing, you can see it goes to multiple colors. And then this is a brightness controlled white light at the end. I'm just moving this. That's about it. If I put it back here, it will start doing the Airbus mode, and then put it absolutely low and it goes cuts off. Sorry. Right. Then other things it gets, which are, of course, if I go here, it will get altitude from the barometer. Now it initialized here. So the way this works is this value is actually tuned based on when it starts. So when it's down, it will get the altitude of that time. This is the heading, And that's basically it. Oh, and external voltage, obviously, which is the voltage of the LiPo and the roll pitch you saw. This is the full menu of what you can send to the receiver on this mod. Right. Now, with that sorted out, I'd like to show you a bit about the actual physical build of this. So, first of all, as you can see, I have it on these legs. Now, this one broke because of a crash, and I sort of just put some epoxy and electrical tape on it. Also, if you're using the F450 PDB, I'd recommend making your own wire bridges. I'll just turn off the lights because it's sort of annoying, and I'll disarm it as well. Now, as you see here, in dry run mode, even if I arm it, it doesn't actually go in turn off the LED. It's in sorry, the OLED instead goes to dry, but in actual flight, it would have turned it off. Right. What I was saying is you should bridge it. So as you can see, I have wires, the thick wires, power wires running and manually bridging all the grounds and all of the power pins. So don't trust the F450's PDB, just do it yourself, because the F450's PDB itself is very unreliable and breaks a lot. That's basically the only real physical thing I wanted to say, other than, well, obviously you have the flexibility to build it as you want. In my case, kept it very sort of modularized, so I can remove anything I want, any of the pins I want. I can change the IMU anytime. So basically this is quite configurable, because obviously I was building it as well, so even I didn't know what the final product was going to be, so I had to keep it configurable. In your case, you can obviously design a PCB or something if you want, because this does fly reliably every time, as long as the hardware doesn't break. So like the software itself is actually good. So one more thing is you should have it on some kind of a foam. So as you can see here, I have it, this is double-sided tape, and then this is a block of foam I cut, and on top of that I have the main IMU mounted, and the other one is actually foam taped. So this is slightly, as you can see, it has wiggles. So both of this is just to simply dampen the vibrations going from the props to the IMUs, so they work more reliably. Yeah, now once that's about it for the hardware, really. I mean, obviously it's free game, you can use a different motors, you can use different sensors, you can do whatever the hell you want, really. That's the kind of the point of this. Now the one thing I wanted to show you is actually the configurator. So if I go grab VS Code back here, you'll find a Python configurator for this, as I mentioned, like this guy. So as you can see here, you'll go into the configurator folder, you'll find the PillFlight. Now just create a venv, install the requirements.txt, obviously standard Python stuff. Now I'll just show it to you, it running. There you go. And when you run it, all the commands are also in the readme of this guy and in the main readme as well. I'm also not going in too much detail about this, because I expect that if someone is trying to build their own flight controller, they'll have some knowledge of basic coding and stuff. So yeah, that's why I'm not going too much into detail. Now as you can see, when I move this live, that is the current tracked heading, which is as you saw here, it's about 197 degrees. That's the live actual heading. That's genuine magnetic north versus what the drone is facing. This is not from where it starts. That is the horizon. Obviously, as you can see, when I tilt the drone, the horizon tilts like it should. Pitch and roll both. These are all the RC inputs, current inputs, aux channels. So the other the other 4 extra channels which you would get, 2 of these you would obviously get normally. 2 of these you won't get normally. Like you wouldn't get any of this in the standard 6 channel version, but once you install the extra software, you'll get this. Here you can see all the numeric values, the sensor biases, so the PIDs. Here you can see everything. This is just to sort of like configure it. Also you can see here what hertz the loop is running at. Now in flight it will run at 200, because if I do the dry run mode, as you can see, it's currently in dry run mode, but obviously according to this it is running in proper mode. This would go to 500 hertz locked as soon as you actually disconnect this and put this in proper mode. So it will turn off the OLED and everything to save time. So the other sensors run at 500 hertz. This shows the mode there. As you can see, I can move it down to horizon and acro. I can change all the things. It updates live. So this is basically just a sort of configurator like Betaflight. Now you can't actually send anything from this to this flight controller, but because I have this here screen which can be controlled completely by the joystick, I felt there's no real need to add that complexity in as well. Yeah, that's pretty much it, I guess, for this. Am I missing anything? Right. Yeah. I don't think I'm missing anything. Oh, right. I would like to show you a little bit more in the config actually once. So if I go back to STM32 IDE. Now, one more thing is you do not need Linux. Obviously, this is a Python configurator and STM32Cube IDE that is being used to program the STM32. So obviously, you do not need Linux. You can run this on any operating system you want, right? These are some of the extra features as well, which I would like to talk about. So first of all, it's a black box, telemetry, battery telem, and divider ratio. So these three are actually pretty much as you would expect. This is telemetry back to the radio. This is the battery divider if you want it on or off. So the reason you'd want it off is for example, if you don't have a battery radio, this guy will still keep shouting because it still reads a false signal. So it will start shouting at you. So just turn that off. And this is the ratio of your voltage divider. If you actually use 2 resistors, just put the ratio there, or you can use off the shelf one like this. Now the reason we need a voltage divider is, if you didn't know already, is the STM32. If you put 12 volts into it, it will completely fry. So you need to lower the voltage down, but you obviously don't care about current or anything. So that's basically why if we use a voltage divider and you set 2 resistors and one small and one big one, then basically because the same amount of current goes through that, the smaller resistor will have less voltage over it. So if you read off of the smaller resistor, and because you know the ratio, you can simply calculate the total voltage across the combo, and based on that, that is your battery voltage. So now you'll have 2 massive resistors. So obviously, because you don't want actually a lot of current being drawn by that, like, so that's why that's a simple voltage divider. I mean, that's pretty obvious what that is. Now the black box is actually a really cool feature. So if we go over here back into VS, now the reason I'm using VS Code for the Python stuff is it's simply simpler, but obviously you can use the normal terminal as well if you wanted. Over here in tools, you'll find a couple of very useful things. So first of all, there's a capture blackbox.py. This is actually a feature that I so far could not find in any STM32 flight controller at all, other than the commercial stuff. This does not have an external SD card, by the way, but there is actually a flash sector on this which is being used to save the last 45 seconds of flight data. So let's say you had a normal flight and then suddenly something went wrong and it crashed and you disarmed it. As soon as you disarm it, you should come here, connect it and run this script. It will actually read that flash sector off of it and get the latest flight data. So it stores everything from motor commands, both the IMUs, what the other sensors are doing, everything it commanded, the current roll pitch, the target roll pitch, etc. at 50 Hertz. So that is being stored into its flash. So in case of a crash, you know what went wrong rather than just having to guess. And this thing actually saved a lot, because during tuning, this is actually very, very useful, because then you can analyze the data rather than having to guess. Other than that, there's a bunch of other stuff. Now I won't go into too much detail about what this is. This is the most important one, but this is actually another useful thing. This is on the bench. Now, as you see in the if you stay till the last of the video, I'll show you my PID tuning rig for this. So that rig, when you have, it is also by the way handmade, you can run this on it, and basically it will give you the vibrations that the flight controller is feeling, so you can tune it accordingly. Now all of this is being well documented both in the code, all the readmes and everything, so I won't go into too much detail. But yeah, I think that's pretty much covers everything about this particular flight controller. And yeah, I hope you guys enjoyed this video. If you did, please be sure to leave a like and go to my GitHub and download the code, and hopefully you guys make some more cool additions to this. And yeah, I'll see you guys next time. Right, small note on the altitude hold thing. I mentioned that, but I completely forgot about it in the video. So the way altitude hold works is actually, so obviously you can't, it doesn't make sense to use throttle inputs when it's in altitude hold mode, because the whole point is you don't use throttle. So the way it works is, let's say it is hovering at a height, which in my case it was hovering, the height it was hovering at, you hit altitude hold. Now what the system itself does, instead of completely disregarding this, if it's in the middle, you can see here there are notches, but basically if it's roughly in the middle, it will start holding at that exact altitude. Put it lower than that, and what happens is it slowly starts coming down in a controlled way, and slowly lands, basically self lands, auto lands. And if you put up, then it slowly goes up proportional to how much how higher, like how much signal you're giving over the middle, if that makes sense to you. So what happened in my case was, when I set it to alt hold, it was the drone was hovering somewhere around this, so it was much lower than the middle point. When I set it to alt hold, I moved the throttle up, which caused it to hover. But as soon as I disengage alt hold, obviously as you can see, the throttle itself is much higher than it should be for hovering, so it instantly goes up. Now this is a bit of a bug. I am not quite too sure about what would be the best way to fix it. If we should like basically not consider throttle for a while, but then it doesn't make sense. If for example in an emergency I need to put it up or down, in a hurry it doesn't make sense to not consider the hover. So I just thought it's best to just leave it, because the worst it does is go a bit high, but then you can immediately put it down and control it. Or like ideally when you are controlling it, you should like put it back down and turn it off. But that's pretty much the it for the altitude hold. And obviously heading lock is just heading lock, it stays in its current heading.